Welcome back to chemistry. And so now what I'm going to be talking about in this presentation is what happened after Dalton formed his atomic theory. And so there were some interesting things that occurred about 80 to 90 years later after he made his theory. And so what happened is we did some experiments and we learned what the structure of the atom is. And so in this presentation, mainly what I'm going to go over is 4 experiments that told us some facts about the structure of the atom. It told us that, 1, the atom is comprised of particles. Some of the particles are negatively charged, which are called electrons. There are positively charged particles called protons, and then there are neutral particles called neutrons. And another important thing that was discovered at this time is that the protons and the neutrons are kind of bundled up in this tiny speck of matter called the nucleus, while the electrons are out buzzing around the atom. So we're going to talk about how the experiments told us that the atom is structured in this way. So this is sort of a timeline of the experiments. You do not need to know the dates at which these experiments occurred. So the first experiment I'm going to go over in just a second was the experiments that determined that atoms are in fact can be subdivided into individual little particles, and one of them is the electron, which is negatively charged. This experiment was done around 1897, and the individual who did it was J.J. Thomson. And then a little bit further on, around 1909, a man named Millikan figured out the actual amount of charge and therefore the amount of mass in an electron. I'll talk about that. Then I'll talk about a very important experiment that occurred in 1911 that showed that the atom was comprised of a very small nucleus that was in the center of the atom, and that the electrons are sort of buzzing around the nucleus. And then later on I'll talk briefly about an experiment that was done by a man named Chadwick in 1932 that indicated that there are neutrons in the nucleus. Let me talk about the first landmark experiment. So this was an experiment that was carried out by a man named J.J. Thomson, and he was working in England. And so what he did in this experiment was he worked with an apparatus called a cathode ray tube. And so there are some pictures of it there, and also there's a schematic diagram that you can sort of look at. So I'm going to talk a little bit about how this works on the next slide. But essentially what J.J. Thomson did is through this apparatus called the cathode ray tube, he was able to determine that the atoms could be broken up into smaller particles. And one of these smaller particles is the electron, which is negatively charged. So let's talk about how he figured that out. So here is a picture or a schematic diagram of a cathode ray tube. And so what it is, it's sort of a large glass tube. And what you can see on the right side of the tube are some metal electrodes. These are just little pieces of metal. One of the electrodes is called an anode, and one of the electrodes is called a cathode. You can see that the electrodes are connected to a voltage source, a large battery. Now, at the end of this glass tube, there is a large fluorescent screen, such that when highly charged particles land on the screen lights up and fluoresces. And so you can detect whatever is landing at that point on the screen. One other important thing to know about this cathode ray tube is that there's no or practically no air in that tube. So right now I'm being struck by molecules in the air, and so that's evaluated by something called air pressure. And so what you'll learn later is that a quantitative measure of the air pressure that is striking me is 1 atmosphere. And in that cathode ray tube, they applied a vacuum pump to pump out as much air as they possibly could. So there are practically no air molecules in it. So the pressure within that cathode ray tube is not 1 atmosphere of atmospheric pressure. It's only 1/1,000,000th of that. So there are very, very few air molecules in the cathode ray tube. So how was this used? Well, what you can do is you can turn on the voltage. And when you do, what the battery will do is it'll impart a strong negative charge onto the cathode and a strong positive charge onto the anode. So the more charge is built onto those electrodes with a higher voltage. So the voltage applied is about 10,000 volts. So as soon as the voltage gets super duper high at that amount, something happens. What happens is you have some kind of particles leaving the cathode. They go through a hole in the anode, they pass through that evacuated tube, and they strike the fluorescent screen. Now, you will know that there are particles striking the screen because the screen will light up at that point. Now, another thing at this time is that we have not applied any external fields to the cathode ray tube, but you can do that and see what effect the external fields have on how the cathode rays are striking the fluorescent screen. And one of the things that J.J. Thomson found is that when you applied an electric field across the cathode rays in the tube, the cathode rays were deflected. So let me talk a little bit about how you create this electric field. It's not so difficult. All you have to do is have two large metal plates that are close together, which are connected to a battery. Once the battery is turned on across those metal plates, you'll get a large positive charge on one plate and an equal amount of large amounts of negative charge on the opposite plate. And what J.J. Thomson noticed is that it looked like this beam of cathode rays is what they're called. These particles are deflected toward the positive plate. And another thing he did was he could apply a magnetic field across the cathode ray tube. And what he found is when he turned on the large magnet, the magnet also deflected the cathode rays, which was interesting because at the time it was known that magnetic fields can deflect charged particles. Magnetic fields do not deflect uncharged particles, but they can deflect positively charged particles or negatively charged particles. And the direction in which the particles are deflected indicates their charge. And also he found is that he could balance the amount of deflection from the magnet but with the electric plates by changing the voltage of the electric plates. So he could sort of manipulate the magnetic field and the electric field so much and so that he could basically deflect these cathode rays to wherever he wanted to on the screen. Okay, so what do these results suggest? So very importantly, one, there were several facts that indicated that those particles leaving the cathode and going through the anode and striking the fluorescent screen, that they were particles of a negative charge. So what are the facts that indicated that? One fact is that these particles didn't so much leave the anode and go to the cathode. Instead, they let the negatively charged cathode pass through the anode to hit the fluorescent screen. So, as you may already know, like charges repel, opposite charges attract. So if you have the cathode is negatively charged, you might expect that those particles that left the cathode are repelled by the cathode and they're also negatively charged. Also, he noted that those cathode rays, those particles, were deflected, and they were deflected in the direction of the positively charged plate. And so that is another indication that those particles in the cathode ray are negatively charged. Also, the data he collected by applying a magnetic field was consistent again that those particles were negatively charged. And so another piece of information which he got, which was extremely important, was by manipulating the level of voltage across those two plates, giving the electric field, and also manipulating the magnetic field and its strength, he could figure out something called the charge-to-mass ratio of those particles. Now, importantly, with this experiment, he did not determine the charge of those particles. He really did not determine the mass of those particles. Instead, he got a charge-to-mass ratio, some number that showed the proportion of the mass to charge of those particles. And so that was very important. And so the number he got was 1.76 times 10 to the 8. That C there is a measure of charge called coulombs per gram. So that was a very important value for further experiments that were done by other people. And then the other thing that he noted was that if he compared the value of the charge to mass ratio of the electron to that of the hydrogen atom, and furthermore, he assumed that both the hydrogen atom and the electron had the same level of charge, it predicted that these particles were only a small fraction in size compared to the hydrogen atom. They were 1/2000th in size of the hydrogen atom. So what the data showed is he could remove particles from atoms and that they would leave, and then these particles were negatively charged, and that these particles were only a small fraction in size compared to regular atoms. So that suggested, importantly, that you could break atoms into smaller particles. He called these particles electrons. Okay, so let me talk about the second experiment that was done to learn more about the electron. And so this is known as the oil drop experiment that was done by a fellow named Robert Millikan. And so in this experiment, what he did was an experiment that was able to tell him what the charge of the electron was. And because we know from J.J. Thomson's work, the charge, the mass ratio, we could learn what the mass of the electron was. But you need to know something about the experiment that he did. So let me go over that with a schematic diagram. So what Millikan basically had was a large can. And inside the can, he had two plates. And those two plates could be electrified, similar to the plates you saw in Thomson's experiment. So one plate could carry a negative charge, and one plate could carry a positive charge. But at the startup of the experiment, those plates were not electrified. But eventually, when he went through the experiment, he did electrify the plates. Now, another thing that he had going into the can was an atomizer. What an atomizer basically is you use it, for example, to spray a plant with water. So you take a spray gun of a container of water and you spray out a bunch of little mist droplets of water onto the plant. That is called an atomizer. And so he had an atomizer attached to the can, except he is not spraying water into this can. He is spraying oil. And another thing is he was able to look what was going on inside the can with a microscope. And so he was able to look at the individual droplets that were kind of falling through the can after they were sprayed or atomized by the atomizer. So here it is. And so he's spraying oil drops into the can. And so what happens is some of them start falling through that small hole. And as soon as he started seeing those little drops going through the hole, he did two things. He turned on the voltage to the can, and also he had a source of X-rays. So what did those things do? What the voltage did was it was attached to those two metal plates. And what happened was the lower plate had a negative charge, and the top plate had a positive charge. Now, he had some kind of device that created X-rays, and what the X-rays did is they took the oil droplets, which normally do not have any excess charge. And for reasons I don't quite understand, the X-rays were to impart extra negative charge on the oil droplets. So while the oil droplets are neutral above the top positive plate, as they fall through the can, they're struck by X-rays and they get a negative charge. Another important thing to notice is that look at where the negative charge is on the lower plate and the positive charge is on the upper plate. So we know that there are negative charges now on the droplets. And so we would expect that like charges repel. So we would expect the lower plate to sort of push the electrons up if possible. So we sort of have two forces going on. Let's consider this drop here. And so one force that is going on is the gravitational force. The gravitational force is pushing this droplet down through the can. But the other force is going on is the force that is created by Millikan by adding extra charge to these oil droplets, which is negatively charged, and also by creating a voltage difference between the plates, which is creating an electric field. And so because the electrons are negatively charged, the electric field force is going up because the lower plate is negatively charged, and so it's going to be pushing the electrons up. And so what he was able to do was adjust the amount of the electric field between the plates such that he was able to balance the electric field exactly with the gravitational field working on that droplet. So he knew they exactly balanced when the droplet was motionless. And so when the droplet was motionless, what he did was he wrote down the amount of electric field he imposed between those two plates to get that drop motionless. And through some simple math, he was able to figure out the value of the charge on the oil droplets. So let's take a look at some of the data he got. What he found was, again, he was able to figure out the relative amounts of charge on the oil droplets. And what you can see, these are numerical values in coulombs. So the values range from 1.6 times 10 to the negative 19 coulombs all the way up to 6.4 times 10 to the negative 19 coulombs. And what you can maybe see is that remarkably, these are not just sort of random numbers. These are discrete values. If you look carefully, all values are integral multiples of the lowest value. The lowest value there is 1.6 times 10 to the negative 19 coulombs. And if you take that number, multiply it by 2, you get 3.2 times 10 to the negative 19 coulombs, which is seen on an oil droplet. And if you multiply it by higher integers, you would see those represented on the chart as well. So what that told Millikan is that that charge on these oil droplets is in discrete integral values, and that they're all multiplied from one base value. That base value is 1.6 times 10 to the negative 19 coulombs. And so this data suggests to him that the one fundamental particle that is imparting this level of charge is the electron. And the level of charge that one electron has is 1.6 times 10 to the negative 19 coulombs. And so from this information, we already know from Thomson's experiment what the charge-to-mass ratio was. And so if we know the amount of charge and we know the charge-to-mass ratio, you can figure out the mass of the electron, and it turned out to be 9.1 times 10 to the negative 28 grams. So at this point, we have two pieces of data that suggest that electrons are particles. And so from this data, J.J. Thomson proposed a model of what the atom looks like. He proposed that you had particles of negative charge called electrons in a sphere of positive charge. Importantly, Thomson did not think that the positive charge was contained in particles. Instead, he thought the positive charge was diffuse throughout the sphere that is containing the particles of negatively charged. So you might ask, well, why is there positive charge in the first place? Why did he have to propose that? And the reason is because it was known that in general, atoms are neutral. They have no excess charge. So he needs as much positive charge as to balance the number of negative particles in this model so that the charges cancel and there's no net charge. But the positive charge is sort of diffuse through the sphere, which is thought to be the atom. He called this model the plum pudding model of the atom. And I'm not exactly sure why he called it that, but apparently this model of particulate negatively charged electrons in sort of a diffuse positive charge is sort of analogous to, say, raisins, which they call plums in English, which I've been told, in a muffin. So that is why it's called the plum pudding model. Okay, so what we're going to talk about now is a new experiment that was carried out by a man named Ernest Rutherford, and he had some people to help him carry out this experiment. And what Ernest Rutherford's experiment showed was that this model was not really a very good description of the atom. So I'm going to talk about this experiment now. But before I talk about this experiment, I need to sort of digress until I talk a little bit about what radioactivity is. And so radioactivity was discovered in around the 1890s, and Ernest Rutherford himself characterized the radioactivity in 1903. And so how radioactivity is created is when you have certain atoms that are not very stable, atoms like uranium or radium they will on their own break apart and release small pieces. These pieces could be parts of the nuclei that were in these elements, or these pieces could be electrons. And so there are really three kinds of pieces that are released. So both uranium and radium and other atoms will release a particle called an alpha particle or an alpha ray. And what an alpha ray or particle is just a piece of the uranium or radium atom. All it is two neutrons bound to two protons with no electrons. It is a helium nucleus. So when these atoms, these relatively large atoms of uranium and radium, release this piece, it's just a very small piece, but it's traveling very quickly. And because it has two protons along with the two neutrons, it is positively charged. Another piece of matter that can be released from an unstable atom is an electron. And so when an atom releases an electron and it goes off into space, this is called a beta ray. And so the particle here is just a high energy electron. And then another piece that is released by atoms is really not so much a particle, but it's really just radiation, a wave that is very high energy, and this is called gamma radiation. Okay, so let me talk a little bit about what the results of the Rutherford experiment were, because that makes it a little bit easier to interpret how this experiment worked to give those results. So one of the things that the Rutherford experiment suggested is that the plum pudding model is maybe not the best model for the atom, and that maybe there may be a better model to describe the atom. Another thing that the data showed is that the atom really is mostly empty space, but in the center of the atom there is a small amount of matter, and that small amount of matter is where positive charge is located. That small amount of matter in the center of the atom is called the nucleus, and another, which I just said right there, and also he proposed that maybe that there are particles in the nucleus that impart that positive charge. Those particles are called protons. And so let me talk a little bit about how this experiment works. So this is the Rutherford experiment. It is also called the gold foil experiment because he used a piece of gold foil to get his results. And so the gold foil he got was not very thick. It was hammered out to maybe be about 1,000 atoms thick. So it's in the center there of that picture. And then surrounding the gold foil is another fluorescent detector. And so again, when you have high energy particles strike the fluorescent detector, it will flash in fluorescence and you can see where the particles are landing on the detector. And also he had there in that box a radioactive substance. It was radium, and the radium is releasing alpha particles. And so let me remind you what the alpha particles are. The alpha particles are really, again, just two neutrons stuck to two protons without any electrons. They are helium nuclei. So they're relatively small particles compared to the size of the gold atom, and they're traveling pretty quickly with a lot of momentum. So what happened was this. The alpha particle emitter, the radium, released alpha particles, and the alpha particles are streaming toward the gold foil, and you can see that in the picture. And what you'll see is that most of those alpha particles are passing right through the gold foil and are not being deflected. And the way you know that is because that fluorescent detector, which is right opposite the source of the alpha particles, is lighting up like crazy. However, you see that some of the alpha particles are being deflected by the gold foil somewhat. But then in rare cases, you have a few alpha particles that are completely bouncing off. It almost seems like they're bouncing off the surface of the gold foil and they're being deflected in the opposite direction. So let's talk about how we can get these results. So here we have sort of a schematic diagram of gold atoms. And so what you can sort of see is that the gold atoms, I'm representing the nuclei with these little dots. And then the rest of the atom where the electrons are are those gold spheres. And what you can see is when you send these alpha particles, which are helium nuclei, through the gold foil, 98% of those particles will not strike anything. They go right through the gold atom where the electrons are. They do not hit the electrons. They go right on through. But occasionally you'll have a few alpha particles that will get close to the nuclei, and they'll be deflected by the nuclei to some degree. And then on the rare occasion, you will have an alpha particle that will directly strike the nucleus and bounce off. Now, we have some interesting information we just gathered. Note that when the alpha particle strikes the nucleus, it didn't get absorbed by the nucleus, it completely bounced off, which tells us the charge of the nucleus. Since we know that the alpha particle is positively charged, again, it is 2 neutrons and 2 protons stuck together, because the nucleus did not absorb that positively charged alpha particle, what happened is the alpha particle bounced off. Remember, like charges repel, so that strongly suggested right there that the nucleus was also positively charged to repel the positively charged alpha particle. And so here is again just a reminder of what the entire population of alpha particles are doing. Okay, so now I'm going to talk about a little bit briefly about the observations of the gold foil experiment. And so, in fact, the actual work was not carried out by Rutherford himself. It was carried out from suggestions by Rutherford, but it was carried out actually by a postdoc and an undergraduate, which later they went on to have good careers. And again, just to recapitulate, most of the alpha particles went through the gold foil without being deflected. A few were deflected, and a few, very small amount, 0.005%, bounced off the gold foil. And there's a famous quote from Rutherford, and he said it was as if a 15-inch shell, which is an armament, a 15-inch shell hit a piece of tissue paper and completely bounced off. And so he was saying, suggesting by his surprise, this was a result he was not expecting, and that this result strongly suggested that because the alpha particles are positively charged, they must be, on rare occasion, striking something pretty solid in the middle of the atom. That thing is the positively charged nucleus. And so from that information, he created a new model. He rejected the plum pudding model of atomic structure. Instead, he said that what is really going on is that it's not so much that the positive charges are dispersed generally throughout the atom. Instead, the positive charges are particles, and they are found completely in a small bit of matter in the center of the atom called the nucleus. This data also suggested that because most of the alpha particles went through the gold foil, that it looks like the atom is mostly empty space. Okay, so let me talk a little bit about how the next particle was discovered, and it was found in the nucleus. So it was known at the time that hydrogen has one positive charge, and that helium, as I kind of talked about earlier, has two positive charges. But there was another fact that they were trying to reconcile with this data, that the helium atom is not 2 times the mass of the hydrogen atom. Instead, it's a lot more. It is 4 times the mass of the hydrogen atom. So how can it be that you have twice the charge in the helium atom, but 4 times the mass? And what Rutherford speculated was that maybe there's another particle in the nucleus which is increasing the amount of mass in the nucleus, but it's not increasing the amount of charge. So this would be a neutral particle. And he suggested at the time that this particle would be called the neutron. Okay, so the last experiment you need to know was conducted by a man named James Chadwick in 1932. And this experiment indicated that the nucleus has a neutral particle. You don't need to know the details of this experiment. Just let me briefly go over it. So what he did is he took a source of radiation, a sample of radium, which released alpha particles, and he bombarded an element called beryllium with it. And what he found was that there were some particles leaving the beryllium what was interesting about these particles is that they were not deflected by an electric field and they were not deflected by a magnetic field, but they were some kind of high energy particle. And so at this time, this was evidence to suggest is that they found a new particle and that was neutral charged. And later experiments suggested that these neutrally charged particles were found in the nucleus. This was known as the neutron. Okay, thank you for listening, and we'll see you next time.